Good morning, dear students. Welcome to another session of digital switching system. So in previous session we had discussed about three-stage network and solved a problem related to three-stage network wherein we had considered m is equal to n. So today let us solve another problem for a case where m is not equal to n. Now consider this problem, that is, design a three-stage network for 100 incoming trunks and 400 outgoing trunks. So in this case, say m is equal to this and n is equal to this case. So what we have is we have the condition m less than n. So just a slight change. So where all we had referred to capital M, we have to replace it with capital N, and capital N with the capital M in the previous condition what we had discussed, because we had derived the equations which were relevant to m greater than n. So based on that analysis we'll move ahead. So in the solution, m is equal to 100, that is 100 incoming, and n is equal to 400, that is 400 outgoing trunks, and it is a expander. So in that is what we have specified. So in all the above equations we replace capital M with capital N and lowercase m with lowercase n. So when we do that, this is what we obtain. That is, if we try to identify the number of cross points, it turns out to be 4473, so approximately, which is near to 4500. Now let us go ahead and see how we can solve this problem related to the given parameters. So here we can see that for the given parameter, we have m is equal to 100 and n is equal to 400. So based on the derivation what we had done, what are the optimum values of lowercase m and lowercase n, that is number of inlets and number of outlets. So it is given by capital M divided by square root of capital M plus capital N, which turns out to be which turns out to be 4.47, and number of outlets turns out to be 17.89. Now we again, as we had done in the previous case, since these are fractions, we cannot have fractional values or decimal values, so these have to be integers which are close to the values what we have identified. Say for example 4.7, we have to the lowercase m value should be close to 4.47, and it should be a factor of the incoming trunks. Similarly for lowercase n, the value should be close to 17.89, and it should be a factor of capital N. So when we identify this, we come across two values, that is for m equal to 4.47, we have two factors, that is 4 and 5, which are factors of 100 and are close to 4.47. Similarly for lowercase n, 16 and 20 are the factors of 400 and which are close to 17.89. Now let us consider the first case. So let us assume that m is equal to 5. So if m is equal to 5, then what are the number of switches required, what are the number of inlets, and what are the number of outlets, and what is the switch size? So instead of going in the tabular form which we had done it for feasibility, we'll just look out how we can do it directly using the diagram. So let us consider the first design case wherein we have considered m is equal to 5. Now if m is equal to 5 and I know that there are 100 incoming trunks, therefore number of primary switches required will be given by 100 trunks divided by 5, so which turns out to be 20 primary switches. So therefore there are 20 primary switches, and since we have to choose a standard switch size of primary, that is we'll decide on 5 by 5 as the switch size of the primary switch. Now since there are 20 primary switches, now there will be a link from each of the switch in the primary stage to to the secondary switch, to each of the secondary switch. So one link from first switch to the secondary switch, second link from the primary switch to the secondary switch, third to the third link to the secondary switch, so on up to the 20th switch. So therefore what this indicates is as many number of primary switches are there, those many inlets will be present for the secondary switches. Now apart from this, how many secondary switches are there? Secondary switches is basically identified by number of outlets of the primary switch. So if you just observe what does this 5 by 5 indicate, that is this 5 indicate is one link should go to one of the primary switch, secondary switch, one link to the second secondary switch, third link to the third secondary switch, fourth to the fourth secondary switch, and fifth to the fifth secondary switch. So by this way we get to know that there are 5 secondary switches. So there are 5 secondary switches, and since 20 inlets are present, let us again choose a standard size for secondary switch, that is, let us choose it as 20 by 20. So if 20 by 20 is the switch size, it indicates that 20 inlets are there and 20 outlets are there for the secondary switch. Now in this case, what does this 20 outlets indicate? This 20 outlets indicates that there are 20 tertiary switches, that is one link for the first tertiary switch, second link to the second tertiary switch, third link to the third tertiary switch, so on up to the 20th link to the 20th tertiary switch. So this indicates that there are 20 tertiary links. But what is the inlet for each of this tertiary switch? So this is given by the number of switches which are present, because I have one link which should be connected, there should be one link which should be coming from each of the switch. So one link from first secondary switch, second link from the second secondary switch, third link from the third secondary switch, fourth link from the fourth secondary switch, and fifth link from the fifth secondary switch. So therefore what this indicates? This indicates that the number of inlets is equal to 5. Now here I cannot decide whether it should be a 5 by 5, because I have 20 switches and there are 400 outgoing trunks. So therefore 400 divided by 20 gives me 20. So this indicates that there should be 20 outlets. So this is a non-standard switch size. So there should be 20 outlets. So that is 20 outlets should be present for each of the tertiary switch. Therefore the switch size turns out to be 5 by 20. So this is what is the design related to m is equal to n. M is equal to 5. So when I take number of inlets to be equal to 5, the number of outlets turns out to be 20, and we had seen that 20 is a factor of 400 and it is close to 17.87. Now if I go for the second design, that is so on the similar basis, if we solve for the other condition, sorry, it has been missed out. So on the similar basis, if I just try to explain, sorry, that diagram I have missed it out. So if I try to just take the other condition, that is m is equal to 4. So here m is equal to 4 indicates that there are 4 inlets, and these have to be divided for the 100 incoming trunks. So 100 divided by 4 turns out to be how much? There are 25 switches, primary switches. Now what does this 25 indicate? That the number of inlets to the secondary switch should be 25. So since this was 4, the switch size what we consider for the primary stage will be 4 by 4, and at this stage the switch size will be 25 by 25 for the secondary. Now since the switch size, that is the number of outlets for the secondary stage, we specify it as 25. So what does this indicate? That this indicates that there will be 25 tertiary switches. there will be 25 tertiary switches. Now if we have 25 tertiary switches, I have to divide it among the 400 outgoing trunks. So each what will be the number of outlets present for each of this. So in this case it will be 400 divided by 25, which turns out to be 16. So that is, if I consider m is equal to 4, I get number of outlets equal to 16. So on the similar basis, we can identify how many number of inlets and outlets should be present for each of the case, and how many how many number of switches are present at each of the stage. So this is the solution for the problem what we have discussed. So continuing with the next this thing. So these are the solutions what we have discussed. Now on the similar basis, we can obtain the results for 4-stage network, as we have discussed for 2-stage and 3-stage. So let us move on further with the next this thing, GOS, that is grade of service for the link systems. So what is basically grade of service? It gives us the probability of occupancy, it gives us the probability of loss for a given system. So as we had discussed in the previous case, that we had a term wherein we had the Erlang first distribution, the Erlang second distribution, so on. So wherein those discussions were done. On the similar basis, if we have different stages of networks, so what will be the grade of service? So that is what we have to look out for. So here we assume that the trunks and the links being busy are independent random events. So what does this imply is, probability of the trunks being busy and probability of the links being busy are two separate entities, and if I want to identify the probability of both of them being busy at a given time, will be actually given by the product of the busyness of both separately, since we have considered it to be an independent random event. Therefore what does this indicate is, it indicates that the probability of both happening at the same time, that is probability of the trunk being busy and link being busy, will be the product of the probabilities of both happening at the same time. So if the two links are connected in tandem, so as we had in 2-stage network and 3-stage network, we saw that we had A links and B links. So that is, we have two stages which are connected. So if that is the case, then what happens to the overall grade of service? Now in this case, let us consider that A and B are the probability of links being busy, that is for the A links and the B links respectively. Now then what does 1 minus A and 1 minus B indicate? 1 minus A indicates the probability of the links being free respectively. Now when I multiply both together, I'll get the probability of both the links being free. Why this we have done is, we are assuming that both the links are independent of each other. That is the busyness, the links being busy or links being free is an independent random event. So because of that, we have the multiplication of the probabilities. Otherwise it would be a conditional probability what we have to consider. Then what is the probability of blocking? That is both the links being busy together at the same time. Now since this is the overall probability of both the links being free, then 1 minus this probability will give us the both the links being busy, that is the links will be blocking the calls. So this is the probability of being blocked. Now what is the occupancy at each stage? It is basically given by the ratio of the total traffic carried to the number of links at that stage. So that is what the occupancy is given by. Now previously we had discussed something related to modes in previous case. That is, mode 1 indicates that we have connection which is required to one particular free outgoing trunk. Then in mode 2 connection is required to a particular outgoing route, but any free outgoing trunk can be utilized. Then third one, a connection can be made using any of the link and any of the free outgoing trunks. So based on these we have different specifications. So let us discuss for 2-stage networks. let A be the occupancy of the links, and since only one link is present between the two stages, that is the primary and the secondary, so we have only A, which is the occupancy of this, and B is related to the outgoing trunks, that is occupancy of the outgoing trunks. Now if we assume that both the occupancies are equal, then in mode 1 the grade of service or the probability of the link being busy will be equal to probability of the loss, which is basically given by the occupancy of the link, which is equal to A. In mode 2, what it specifies is any free link can be used, so we have to identify what is the overall grade of service. Now here the probability of loss of a particular link is given by 1 minus of A into 1 minus of B. So this is as per the previous slide what we had discussed. So the probability of loss, which is nothing but the probability of blocking in our case for that particular link. Now since there are G links available, that is G paths available, then the probability of blocking of each, if they are independent random events, then it gives us the overall grade of service for the two-stage network. Since they are independent random events, it will be equivalent to multiplying this G number of times, that is probability of loss of each link, multiplying probability of loss of each link. So therefore what it specifies is B2 will be equal to this probability of loss raised to number of paths which are possible, or number of links which are possible. In this case, number of links possible is given by the number of secondary switches. So therefore this is the loss probability of loss or grade of service in mode 2. Now when we go to mode 3, then connection can be made to any of the free outgoing trunks, so it is a independent, all the links and the paths and the trunks are independent, and probability of them being blocked is also an independent random event. Therefore when we try to identify the probability of loss for mode 3 condition for two-stage network, it gives us the first Erlang distribution equation, that is probability of all the links and all the trunks being busy, so which is equivalent to E of 1 comma n of A, which is the grade of service for mode 3 for two-stage network. Similarly for three-stage network, if A is the occupancy of A links, B is the occupancy of the B links, and next we have the outgoing trunks, that is C, which is the occupancy of the outgoing trunks. Then under mode 1, when we are choosing only one particular outgoing link, we have to identify the probability of that particular link being busy, so which will give me the grade of service for the three-stage network. Now this is determined separately based on the A and B links. Now what we have is the probability of both links being free, as discussed previously, will be 1 minus A into 1 minus B. Therefore probability of both being occupied or the probability of blocking will be equivalent to 1 minus of this value. So which and if we have G2 number of secondary switches, then the probability that all G2 independent paths are simultaneously blocked is identified as B1. Then what it specifies is it gives us a grade of service which is nothing but this term, that is probability of blocking multiplied G2 number of times. So that is what is the value we'll be getting. Now if we have for mode 2, so when we go to mode 2, the probability of blocking, that is B1, in mode 2, what is the specification? We can use any of the link, but we have to go for one specific outgoing trunk. So in that case what happens is since B1 is already identified, that is probability of blocking in the mode 1, so in order to estimate the overall probability, this is 2, in order to estimate the overall probability of loss or grade of service, it is given by this 1 minus B1, which gives us the probability of blocking, into 1 minus C, which is gives us the probability of blocking of the trunks. And since G3 number of switches are present in the tertiary stage, the all switches being blocked will be given by the product of this 1 minus B1 into 1 minus C, this multiplied G3 number of times, so which will give me the probability of blocking or the grade of service for three-stage networks in mode 2. Now for mode 3, all the links and all the trunks should be occupied. So this is given by again first Erlang distribution. So this is it for the digital switching system module 3, that is telecommunication traffic and switching system. So thank you for your patience hearing. Thank you, and this is the end of the session. Let us meet for the next session for module 4 and 5. Thank you.